Hello everyone, this is Moin Ali Naqvi from Simula Research Lab in Oslo, and today I'm going to present our artifact paper, which is Chess, a framework for evaluation of self-adaptive systems based on chaos engineering. Let's start with an outline of the presentation. So first of all, I will present the motivation of this research. I'll give some background and I'll explain our approach and then implementation details, and I'll show you a demo of our artifact, and at last I will conclude this presentation. Let's start with motivation. First of all, there is a lack of systematic evaluation methodologies. Secondly, most of the evaluation methods that already exist are based on the models for designing those systems, and they may not perform very well for the runtime layers. Further on, some of the self-adaptive and self-healing systems may have machine learning or AI components or components that are black box in nature. So evaluating those methods can also be challenging. Then the adaptation strategies of self-adaptive and self-healing systems can vary from system to system. And last but not least, many of these self-adaptive systems adapt and may show emergent behaviors which might not be considered at the time of designing these systems. Moving on to our approach. So most of you would be aware of MAPK feedback loop. So in our case, we extend traditional managed and managing system with system self-monitoring and a fault injection component that helps the evaluation process. And I will explain later how these components come into play in terms of evaluation. This is a background for chaos engineering. So the general concept of chaos engineering consists of multiple steps. So in order to perform a chaos engineering experiment, we first need to define our hypothesis about the steady state. And once we know how a steady state of a system is, we introduce chaos into the system and check whether the system is performing according to its behavior or is deviating from the normal behavior. And at last, we roll back chaos. So generally, this happens in a more iterative way, and along these experiments, we are monitoring the system to check how the system is deviating. So some of the potential areas for weaknesses in a system can be linked to people, processes, practices, applications, platforms, infrastructure. In our case, we have looked for several types of faults, which I will explain later on. Moving on, this is the process flow for our approach. So there are various steps. Let's start with the designing of a chaos experiment. So as you have seen in the previous slide, we start with defining the steady state, and we build a hypothesis about the normal behavior of the system. And through that, we design our chaos experiment. So we end up with a pool of experiments. And we chose some of these experiments from the pool, and then once these experiments are selected, we inject those faults into the system, and meanwhile we check the steady state. And while we are doing that, we have the monitoring systems or monitoring tools that generate different types of logs, and these logs can then be used for the evaluation of the system. And we evaluate the system according to what the user requirements for the system are, or what kind of quality attributes we are evaluating. And once we have an evaluation result, we can use this to create evaluation feedback. So this evaluation feedback can then further be used to design chaos experiments. So this process can be run in an iterative way. So you can see here some of these steps are runtime and some of them are design time. So here you can see the implementation architecture for our deployment, and we have used Kubernetes environment. This shows like all the services that are deployed, and along with that we have a load balancer that is used to communicate with the services outside of Kubernetes. Then we have the Istio injection enabled, and we have monitoring tools like Prometheus, Grafana, and Kiali. And outside the Kubernetes cluster, we have the user interface service, we have data storage, and we have the monitoring user interface where we can see the logs and the health of the services. And similarly, we have the system manager that acts as a managing system, which has the ability to heal the system or recover it from errors. And we have a fault injection module, which can be used for injecting faults. And this also generates chaos logs along with the system monitor. So in order to test our approach, we have used two demo applications. First of all, we have Yelp, which is an open source application. Here you can see the Istio view of the service graph. So it consists of a UI, a Redis server, a Yelp DB, and there is an application server. So from the UI, you can vote for different items, and using that, traffic flows from the app server to the DB. Second, we have our smart office case study that we have developed by ourselves. So this consists of a number of services like temperature service, motion service, external weather service, and this simulates an office environment. And there are like number of requirements that the system needs to fulfill, like temperature of the office, the level of lighting, like according to the user requirement. Moving on, this slides explain how to use the artifact. So the artifact is available for everyone to use as a virtual machine. So on the left side, you can see the directory for the artifact. Here, there are like files for the starting of the cluster, then the smart office application, the Yelp application, and then in the chaos folder, you will find like some specific scenarios, which I will explain in the next slide. And then we have system manager and system monitor. Here you can see like the number of steps you can perform, you can follow to run smart office scenarios or Yelp scenarios. These are also available in the README file along with the virtual machine. So further, the test scenarios we have used for the fault injection. So we have used like 5 different scenarios, and we have discussed it in the paper, our approach in terms of choosing these scenarios. So we looked at like most commonly occurring faults within microservices system, and we chose these kind of faults. So we, for example, we look at like how a deployed sensor can get down, or it can send erroneous readings, or if like a running service can have a high level of request rate. And for running each of these scenarios, we have files in the artifact which you can use. Here you can see like a mapping of these all 5 scenarios along with the level of faults that needed to be executed, and then which applications are affected. And on the right side here, you can see like a template for a chaos engineering experiment. So if someone wants to run their own experiments, they can choose they can use this template to create their own chaos experiment. In the next slide, I will show you the demo for our framework. So here you can see like for the scenario 1. So first of all, like this is the README file, and we open a new terminal, and we are just following these instructions. So like first of all, we are running a new terminal, and then we are creating the cluster. Generally, it takes 2 to 3 minutes, but in our case, we have fast forwarded it to save some time. So here you can see that the Kubernetes clusters are deployed successfully. So now we are going to run the system monitoring and system manager services. So here, when we have run this command, here we can see the system manager running. So this will use as a self-healing system. So whenever there is like a fault injection happening, this may intervene and like recover the system from the failures. Here you can see like it's creating all the services required for the application to work. Now we run a new terminal for running the chaos script. So we chose like one of the files. First of all, we go into the directory, and then we will choose the scenario 1, and then we will run. So we are still waiting because some of the services are not ready yet, like the system for the for the smart office is getting ready. So now we see that all the services are ready. And now we go to the file, run the kiosks. And here you see like these number of like data corruption scenarios happening. And here you see like the system has detected that there were failures and it has recovered the system from that. Now what we do is like we terminate the system manager. So now there is no self-healing service running. And now we run the same chaos injection experiment again. And now the same types of faults are injected, and here you see like the system showing some warnings, but then there is no system manager right now. So you see the system not being able to recover from the failure, and it's like one type of error leading to another, and it's running into the cascading failure. To conclude, this artifact that I presented contains predefined functional and infrastructure level fault injection scenarios. We have system self-monitoring service, which provides us with extensive logs. Similarly, we have the system managing service that reacts to the abnormal behaviors and like attempts to recover system from these failures. And this artifact also presents a comparison of system failures, different types of system failures, and cascading effects these demo applications may run into. So in general, this artifacts provides support for systematic evaluation of new approaches. Anyone can easily modify this artifact. Anyone can perform evaluation for their applications. And on the right side, you can see a QR code for replication package on Zenodo. And you can find a full-length YouTube video with the QR code down on the right side. Thank you so much for listening to this presentation, and feel free to ask any questions.